All right, picking up where we left off. Color. Color is ubiquitous, obviously, it's everywhere. Um, it's arguably as important to our lives as notes to music. Um, you probably consume a lot more color than you do sound, in that sound being typically marked as music. And unlike music, well, that's not always the case, but most of the time in music, we listen to it, or we listen to it and understand that we do or do not like it. Um, in terms of colors, we tend to ignore most colors unless they stand out. But they do define our lives, in fact. Um, from anything like fashion to seasonal affective disorder, color can be a big issue, right? Um, the human eye in terms of color is far more sensitive than a computer or camera. That said, 17 million different variations using hex codes is pretty great. Um, there's subtle variations to eye for the eye to signal depth, movement, texture. Um, so we are by definition limited when we are trying to make visualizations in data, but what we can do is a little bit of trickery. Um, I've already shown you just some basic ones, right? Manipulating hue, value, intensity, these kinds of things are what's going to be key for you. Again, hue breaks down to, or color breaks down to hue, intensity, and value. Intensity can sometimes be called chroma, and value can sometimes be called luminance. But hue is the color choice or the wavelength. Intensity is the range between the pure color and its grayscale, and the value is how light or dark something is. Right? And again, tinting means to add white. Shading means to add black. And feel free to mock anybody who ever speaks of tinted windows, unless in fact the car or truck or whatever it is they have actually has white windows. Um, and R, we're going to use hex codes, but RGB, red, green, blue, notation is also going to be used. I showed you in the previous part on color theory one of these sort of color theory rectangles. Here's another. If you stare right down the center of this and just sort of meditate on it for a second, the colors, the rectangles in the middle, the small ones, are going to start to separate, and the one on the left will turn purple, and the one on the right will turn pink. Again, that is a color interaction. It is not just the color interaction with the field color underneath. It is also an interaction between the field colors. You can do a lot of weird tricks with this kind of stuff. And in graphics and visualizations, color interaction is sometimes subtle, but it's definitely a big deal. All right. There's lots of stuff going on in R to help you with colors in addition to just creating your own palettes. RColorBrewer and colorspace are very helpful. The kinds of palettes that you're going to want to create might include sequential palettes, diverging palettes, and qualitative palettes. Obviously, for example, qualitative palettes would go with a variable that is qualitative. If you've ever seen a globe that isn't sort of a topographical globe, and you look at, let's say, the United States, and then you see the states, and they're just sort of randomly colored states, right? And it's the geopolitical boundaries, and there's no, landmarks or anything like that. That's a qualitative palette because it's assigning a color based on categories, right? A diverging palette could be something like red on one end, blue on the other, and white in the middle, or something like that. That might be useful if you were mapping, let's say, I don't know, political ideology, and it's on a continuous scale, let's say, from like -10 to +10, where 0 is a centrist, -10 is most liberal, and 10 is most conservative, or something like that. And it's actually measured in qualitatively and not, or quantitatively, I'm sorry, and not qualitatively. And then we also have sequential palettes that would appropriately show something like an ordinal variable, right? Or maybe even um, a continuous variable, but just one variable in its range, and there's no true center to it, right? Something like that would be useful. So, like dark purple to light purple, something like that. But our RColorBrewer and colorspace packages are really useful. Um, we're going to learn how to set up our own palettes and use hex codes and RGB and translate between the two. Um, Again, 17 million almost of combinations there. And these are a couple of pieces of code in R that translate from RGB to hex and hex to RGB. One of them requires a package, and the other one is in base R. But both of these lines actually represent the same color, just in RGB in this case and in the hex code in this case. All right. Again, RGB is represented by 3 sets of integers. They each go from 0 to 255. They're the same number of combinations as with hex codes. Hex codes are 6 alphanumeric characters, 0 to 6 and A to F. And ggplot handles these very well, and you should really take advantage of these and create your own fantastic scales as a result. Let's take these ideas and let us turn them into principles, all right? So you want to make choices first that highlight the variation in your data. First of all, your data need to vary. Things that you're trying to show need to actually have variation in them. What is the story that you're trying to emphasize correctly? You want to really be mindful of colors and their grayscale values. It could be something like you're wanting to be mindful for color blindness, but it could also be mindful of colors that and how they might translate to grayscale in the case that your viewers are going to see it in gray or black and white or a variation in gray as opposed to the actual colors that you want. Now, if it's just going to be a digital thing, it's going to be online, it's not a big deal. But if it's on paper, then it might actually be a case that where people might see it just as often in grayscale. So like red and green, for example, pure red and pure green in color theory, in their pure forms, are actually the same gray. Now, that's not something you would necessarily think about being true, but it is. You want to balance the intensity of your colors. You don't want to be too boring, but you don't want to be purely intense because that can be overwhelming and it can drown out the story that you're trying to tell. Where you want to be is somewhere between probably 50 to 80%. It's a rule of thumb. There's no answer, but you don't want to have boring colors, but you want to have colors that you've dialed down the intensity at least a little bit because it can be too much. Again, colors interact. This takes practice. We could do a whole class just in color theory, but we're not going to. And then you always need to check your final plots outside of R to make sure different display setups and how they end up showing, because they'll emphasize colors in different ways potentially. Your assignments based on these things, you're going to be able to do 2 things. First, you're going to be able to recreate the Playfair plot from slide 6. This one. And it's from scratch, including the data. And this is just for bonus points. In addition, you may also create color theory rectangles like the ones I've shown you, like this one, where you take one color and make it look like 2, or you take 2 colors and you make it look like 1. And if you want, you can also try making a color look transparent. I strongly suggest you changing the rectangle format, but you will have the code that I've given you so that you can change the rectangles. They'll be due May 12th by midnight if you choose to do any or all of them. So I strongly urge you to give it a shot. And in the next video, I'm going to break to R and show you some of these things.